Hello everyone, my name is Namrata Verma, Assistant Professor in the Electronics and Telecommunication Department at Sri Santosh Rungta Group of Institution, Rungta College of Engineering and Technology, Bhilai, Chhattisgarh. In previous lecture, we discussed about quadrature phase shift keying, that is QPSK, its generation, detection, advantages and disadvantages along with application of QPSK. In today's lecture, we discuss M-array PSK, why this M-array PSK is required and what are the differences between M-array PSK and PSK. In this lecture, we cover the topic with the following points, which are: first, we see the objective of this lecture, then the introduction to M-array PSK, then signal space diagram, then why M-array PSK is important or required, then M-array PSK transmitter, M-array PSK receiver, drawbacks of M-array PSK, application and comparison of M-array PSK with BPSK and QPSK, and at last summary of this lecture. Now, let us see the objective of this lecture. First objective is to educate the learner on the fundamental principle, technical details and practical application of M-array PSK as a digital modulation technique, and then to provide a clear and comprehensive understanding of M-array PSK, including its advantages, implementation and role in modern communication system. Now, let us see first introduction to M-array PSK. M-array phase shift keying, that is M-array PSK, is a digital modulation technique which is used in communication system to transmit data by changing the phase of the carrier signal. In M-array PSK, the carrier signal take on one of m possible phase shift, where m is an integer greater than 1. The relation between the number of bits per symbol, that is n, and m is log base 2 m. Each of these carrier phase shift represents a unique digital symbol which allows m symbols to be transmitted per modulation interval. The most common form of M-array PSK are BPSK, QPSK and 8PSK. Binary PSK, that is BPSK, have two possible phase shift representing 1 bit per symbol, as we discussed it in previous lectures. Quadrature PSK, that is QPSK, have 4 possible phase shift that representing 2 bits per symbol, that also discussed in previous lecture. 8PSK system have 8 possible phase shift representing 3 bits per symbol. By using PSK, we are limited in the uses of symbols and number of bits. In order to increase the capacity of channel, we use M-array PSK. M-array PSK provides higher spectral efficiency compared to simpler modulation scheme like on-off keying, as it transmits more bit per second in the same bandwidth. In binary phase shift keying, that is BPSK or 2PSK system, we have two symbols, either 1 and 0, and phase shift of sinusoidal carrier is switched from one value to other corresponding to change from 0 to 1 or from 1 to 0 in the digital data. As in BPSK, number of symbols m is equal to 2, that may be either 1 or 0, and number of bits n per symbol is equal to 1, having phase shift of 180 degree. In quadrature phase shift keying, that is QPSK or 4 PSK system, 2 bits are modulated at once. Therefore, in QPSK we have 4 symbols, either 0 0, 0 1, 1 0 and 1 1. As in QPSK, number of symbols m is equal to 4, number of bits n per symbol is equal to 2 and phase shift between two symbol is 90 degree. It select any one of 4 possible carrier phase shift, that is 45 degree, 135 degree, 225 degree and 315 degree. Out of these 4 phases, it will select any one phase shift in carrier. In case of 8 PSK, 3 bits are modulated at once. Therefore, in 8 PSK, we have 8 symbols which are 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. In 8 PSK, number of symbols m is equal to 8, number of bits per symbol n is equal to 3 and phase shift between two symbol is 45 degree. In 8 PSK, efficiency and capacity is increased by 3 times. Now, let us see the bandwidth for M array PSK. These diagram represent the spectrum of BPSK. Here, the center frequency of Fc and upper frequency is Fc plus Tb and lower frequency is Fc minus Tb, where Tb is the bit duration or time period of one bit. Here, upper frequency is Fc plus 1 upon Tb. The term Fc is used as carrier signal cos 2 pi Fct is modulated according to digital signal, where bit duration is Tb. As we know that the bandwidth can be defined as difference between upper sideband and lower sideband or upper frequency and lower frequency. Therefore, bandwidth is equal to Fc plus 1 upon Tb minus Fc minus 1 upon Tb, or after simplification this bandwidth is equal to 2 upon Tb, or which can be also written as twice of Fb, as we know 1 upon Tb is equal to Fb. Similarly, we can find the bandwidth of QPSK. These diagrams represent the spectrum of QPSK. Here, center frequency is Fc, the upper frequency is Fc plus twice of Tb, Fc plus 1 upon twice of Tb, and lower frequency Fc minus 1 upon twice of Tb, where twice of Tb is bit duration or time period of 2 bit or 1 symbol, as in QPSK 2 bits are transmitted at once. Therefore, bandwidth is equal to Fc plus 1 upon 2 Tb minus of Fc minus 1 upon 2 Tb, or after simplification it will be 1 upon twice of Tb plus 1 upon twice of Tb, that will be equal to 1 upon Tb or Fb. So, for QPSK bandwidth is Fb and for BPSK bandwidth is twice of Fb. So, in QPSK bandwidth is decreased. Similarly, let us see the bandwidth of 8 PSK. These diagrams represent the spectrum of 8 PSK. Here center frequency is Fc and the upper frequency is Fc plus 1 upon 3 TB and lower frequency is Fc minus 1 upon 3 TB, where 3 TB is bit duration or time period of 3 bit or 1 symbol, as in 8 PSK 3 bits are transmitted at once. Therefore, the bandwidth of M array PSK will be Fc plus 1 upon 3 TB minus of Fc minus 1 upon 3 TB, or 1 upon 3 TB plus 1 upon 3 TB, that is equal to twice of or 2 upon 3 TB, or it can be written as 2 by 3 FB. So, as we increase the value of M, that is n times of TB, the bandwidth is reduced. Now, let us see the phase shift of M array PSK. The general formula for M array PSK is given by phase shift is equal to 2 pi upon number of symbols, or 2 pi upon capital M, where M represents the number of symbols and duration of each symbol, that is Ts, is equal to n times of TB, where n represents the number of bits transmitted in one symbol and TB represents the bit duration. Therefore, the phase shift for BPSK, that is M is equal to 2, as in BPSK we have only two symbol, either 1 or 0. Then the phase shift will be 2 pi upon 2, that is pi or 180 degree. For QPSK we have M is equals to 4, that is we have 4 symbol, that symbols are 0 0, 0 1, 1 0 and 1 1. Therefore, phase shift will be 2 pi upon 4 or pi by 2 or 90 degree. Similarly, for 8 PSK, M is equal to 8 and the phase shift will be 2 pi upon 8, that is pi upon 4 or 45 degree. Therefore, we can conclude that by increasing the value of M, the phase shift will be decreased. Now, next is signal space diagram. In digital communication, a signal space diagram typically refers to a constellation diagram that visually represents the different possible states of a modulated signal in a two-dimensional space. It is the graphical representation of modulation technique. This diagram is crucial for understanding how symbols or combination of bits are mapped to signal states in various digital modulation scheme such BPSK, QPSK and M array PSK. The standard expression for M array PSK is given by V of t, that is equal to under root 2 PS cos 2 pi FCT plus phi m, where phi m represents the phase shift and m is equal to 0, 1, 2 up to m minus 1, and that phi m is equal to 2 m plus 1 is multiplied by pi and whole is divided by capital M. By applying the trigonometric formula in the above equation, the expression of M array PSK will be V of t, that is equal to under root 2 PS cos phi m t into cos 2 pi FCT minus under root 2 PS sin phi m t into sin 2 pi FCT, which can be also written as Vt is equal to under root Ps into Ts cos phi m into phi 1 t minus under root Ps into Ts multiplied by sin phi m into phi 2 t, where phi 1 t is equal to under root 2 upon Ts cos 2 pi f c t, and phi 2 t is equal to under root 2 upon Ts multiplied by sin 2 pi f c t, or V t will be equal to under root Ps into n times of Tb, where Ts can be replaced by n times of Tb, cos phi m t into phi 1 t minus under root Ps into n times of Tb into sin phi m into phi 2 t, or V t can be also represented as under root Ps into Tb into under root cos phi m minus phi 1 t minus under root Ps into Tb into under root n sin phi m t into phi 2 t. In signal space diagram, all the m points are placed in a unit circle and each is separated by 360 degree or 2 pi divided by m apart. This figure represents the signal space diagram in which there are m number of signal points from V0, V1, V2 up to Vm minus 1, and each are separated by 2 pi by m. For BPSK, we have m is equal to 2 and there will be only 2 signal points or symbols with phase shift of 180 degree. For QPSK, m is equals to 4 and there will be 4 signal point or 4 symbols with phase shift of 90 degree. The signal space diagram is used to analyze the signal properties, evaluate error performance, to illustrate the noise effects, etc. Now, next is why we are considering or using M-array PSK. The M-array phase shift keying, that is M-array PSK, is required in digital communication system for several important reasons related to data rate, bandwidth efficiency, system design flexibility, and here is some reason why we used M-array PSK. The first one is increased data rate. By increasing M-array PSK allows each symbol to represent more bits of information. For example, QPSK transmit 2 bits per symbol while 8 PSK transmit 3 bits per symbol. These higher bit per symbol ratio increases the data rate without requiring the additional bandwidth. Efficient use of bandwidth. In communication system where bandwidth is limited, M-array PSK provides a way to transmit more data within the same bandwidth. Next point is spectral efficiency. M-array PSK is more spectrally efficient than binary PSK BPSK because it can transmit more bits per symbol, allowing for higher data without increasing the occupied bandwidth. M-array PSK can be adopted to different system requirement. By selecting an appropriate value of M, engineers can balance the data rate, bandwidth and noise tolerance according to the application. Now, next reason is reduced bandwidth requirement. Bandwidth of M-array PSK is reduced because M-array PSK transmits more bits per symbol. It can achieve a higher data rate within a given bandwidth compared to lower order modulation scheme like BPSK. Then the next reason is trade-off between performance and complexity. M-array PSK allows designers to choose a modulation order that best suits the needs of communication system, which gives flexibility to select a value of M. M-array PSK system have the ability to scale number of symbols M which allows systems to adapt to different channel condition and requirements. Now, next is application in various communication standards. M-array PSK is used in a wide range of communication standards including mobile network like 3G, 4G, 5G, in Wi-Fi, satellite communication and digital TV, which makes it more versatile. Now, next point is error performance. In conjunction with error correcting code, M-array PSK can provide a good balance between data rate and error performance, making it suitable for wide range of applications. Although higher order M-array PSK scheme require more accurate phase synchronization, advances in digital signal processing and error correction have made it feasible to use even higher M values in practical systems. These are the points because of that the M-array PSK is used in wide range of applications. Now, let us see the M-array PSK transmitter. First, the bit stream BT is applied to serial to parallel converter. These blocks form a symbol of n successive bits, that is the output of serial to parallel converter in n bit word. These n bit per symbol have been presented in parallel form. The output of serial to parallel converter remains unchanged for duration n times of TB. For example, let we have bit stream BT is equal to 10, 110, 110 passed through the serial to parallel converter and n is equal to 2, that is in BPSK. Then the bit stream is that is in QPSK. Then this bit stream is grouped in 2 bit at a time, like 10 is the first symbol, 11 is the second symbol, 01 is the third symbol and 10 is the fourth symbol, and these symbols are transmitted in parallel form. In case of QPSK, n is equals to 3 and 3 bits are grouped together and the symbols will be formed. The n bit output of the converter is then applied to the digital to analog converter. Depending to the n digital input, it produces the analog output m of t. The digital to analog converter output remains unchanged till last nth bit is received. Depending on the input n bit, the output of D to A converter is decided and this output is m of t. Again, serial to parallel converter starts taking bits for next n word. The n bit digital input can have 2 to the power n, that is equal to m number of possible combination. Therefore, D to A converter output m of t will have m number of different values depending on the symbols. The analog voltage is applied to a sinusoidal signal generator which produces a constant amplitude sinusoidal output voltage. The phase phi m is varied according to the value of the symbol, which is determined by D to A converter output. Thus, at the output of transmitter, we get a fixed amplitude sinusoidal waveform, the phase of which has one of the corresponding of n bit symbols. The phase of sinusoidal output will change only once per symbol time, that is Ts is equal to n times of Tb. In this way, M-array PSK signal will be generated. Now, next is M-array PSK receiver. These figures represent the block diagram of M-array PSK receiver. First, the M-array PSK signal is received, then the carrier recovery system will raise the signal to mth power. As we have number of symbol is equal to m, then it will raise the signal power by m. For example, in BPSK, signal power is raised by factor of 2. This signal is applied to band pass filter having a sender frequency of m times of f naught, and it will allow the frequency from m f naught minus f c to m f naught plus f c, and rest of the frequency term will be rejected. At filter output, we get the sinusoidal frequency m times of f c, that is mth harmonic of carrier frequency f of c. For example, in BPSK, we will get twice of f c as m is equal to 2. Now, this frequency is divided by m to obtain carrier frequency f c, then 2 carrier produced at the output, which is cos 2 pi f c t and sin 2 pi f c t. In this way, carrier frequency is generated at the receiver side, and this is the same carrier which was used at the transmitter side. Therefore, this type of receiver is called coherent receiver. These recovered carrier are applied to 2 multiplier, and other input to each of the multiplier block is connected to the received M array PSK signal, that is S of t. The output of 2 multiplier, that is S t into cos 2 pi f c t and S t into sin 2 pi f c t, are applied to integrator. The integration is from 0 to n times of Tb. So, for BPSK, m is equals to 2 and n is equals to 1. Therefore, in BPSK, integration is from 0 to Tb, where Tb is the duration of one pulse. The output of integrator is proportional to even part, that is Ps into Ts into Pe, and odd part, that is Ts into P naught. These output are then applied to an analog to digital converter, which gives the digital n bit transmitted signal, and this signal is recovered into Bt by using parallel to serial converter. Now, in the previous slide, we already seen the advantages of M array PSK in the slide why we are using PSK. Now, next we will see the drawbacks of M array PSK. The first is noise immunity. The noise immunity of M array PSK is decreased by factor of 2, which are high error rate and sensitivity to phase noise. As m increases, the phase difference between adjacent symbol decreases, making the system more susceptible to noise and phase error. This leads to the higher bit rate for the same signal to noise ratio compared to lower order PSK scheme. The M array PSK signal is sensitive to phase noise, especially at higher values of m, as the closely spaced constellation points can easily be misinterpreted. Now, next is the complexity for high m values. The complexity of the receiver increases with the number of phase states, as it needs to accurately detect the phase of the received signal, especially in the presence of noise and fading. The M array PSK signal has low power efficiency due to increased power requirement, amplifier linearity and the phase synchronization. To achieve the same bit error rate as lower order PSK scheme, M array PSK require a higher transmit power, particularly for large m values. This reduces the power efficiency of the system. Now, next is the M-array PSK signal require highly linear amplifier, especially for large M, to avoid distortion, which can further degrade signal quality. Next is the higher order M-array PSK scheme require precise phase synchronization between the transmitter and receiver, increasing the design complexity. The next drawback is M-array PSK is limited by channel conditions. The M-array PSK is more vulnerable to channel impairment such as fading and multi-path effects, particularly in mobile communication environment. Now, next slide is application of M-array PSK. The M-array PSK is used in wireless communication like in cellular network and in satellite communication. In cellular network, the M-array PSK, particularly 8 PSK, is used in GSM and EDG network to provide higher data rates while maintaining compatibility with existing infrastructure. M-array PSK is commonly used in satellite communication system due to its bandwidth efficiency and ability to handle large data rate. The M-array PSK is used in digital television and radio broadcasting. In M-array PSK, such as QPSK is used in satellite television broadcasting, for example, DVB, that is digital video broadcasting, to deliver digital TV content efficiently. M-array PSK schemes are also used in digital radio standards like digital audio broadcasting to provide high quality audio over limited bandwidth. Now, next application is it is used in modern technology. The M-array PSK is employed in modems for data transmission over telephone lines, particularly in the early days of internet where bandwidth efficiency was critical. Now, next application is military and secure communication. M-array PSK is used in military communication system where bandwidth efficiency and the ability to transmit high data rates in a secure manner are essential. It is also used in satellite and space communication. M-array PSK is used in a telemetry and command system or control system for spacecraft and satellites where efficient use of the limited bandwidth is crucial. Now, next we see the comparison of M-array PSK with BPSK and QPSK. Comparing binary phase shift keying, that is BPSK, quadrature phase shift keying, that is QPSK, and M-array phase shift keying, that is M-array PSK, involves the comparison of key aspects such as modulation efficiency, bandwidth uses, complexity and noise performance, etc. Let us see the detailed comparison. First is modulation order. In BPSK, M is equal to 2, that is it have 2 phase states. In QPSK, M is equal to 4, that is it have 4 phase states, and in M-array PSK, M can be 8, 16, 32, etc., where M is the phase state. The second parameter is bits per symbol. BPSK have 1 bit per symbol, QPSK have 2 bits per symbol, while M-array PSK have log base 2 M bits per symbol. For example, 8 PSK have 3 bits per symbol, 16 PSK have 4 bits per symbol, and so on. The third parameter is bandwidth efficiency. BPSK signal have lowest bandwidth efficiency since it transmit only 1 bit per symbol, whereas QPSK signal have higher bandwidth efficiency than BPSK as it transmit 2 bit per symbol. And M-array PSK signal have higher bandwidth efficiency as M increases, allowing more bits to be transmitted per symbol. However, increasing M also increases the required signal to noise ratio for reliable communication. Now, next parameter is constellation diagram or signal space diagram. In BPSK, there are two signal points on the unit circle which are 180 degree apart, whereas in QPSK, 4 signal points are on unit circle which are 90 degree apart, and in M-array PSK there are M points on the unit circle, each separated by 360 degree divided by M. As M increases, the points are more closely spaced, making system more susceptible to noise and phase error. Next parameter is noise immunity and bit error rate. The BPSK system have best noise immunity among all the three. It has the lowest bit error rate for a given SNR because the phase difference between symbol is 180 degree. Whereas in QPSK, system have slightly worse noise immunity than BPSK, but better than higher order M-array PSK scheme. The phase difference between adjacent symbol is 90 degree, which is still relatively robust to noise. But in M-array PSK, as M increases, noise immunity decreases and the bit error rate increases for the same SNR. The phase difference between adjacent symbol decreases, making the system more sensitive to noise and phase distortion. The next parameter is complexity. BPSK is simplest modulation scheme which is easy to implement, requiring the least complex transmitter and receiver designs, whereas QPSK is more complex than BPSK as it requires the generation and detection of 4 different phase states. However, it is still widely used due to its balance between complexity and performance. In M-array PSK, complexity increases with M because of the need for more precise phase synchronization, more complex signal processing and tighter error correction algorithm. For example, 16 PSK is more complex than 8 PSK. Now, next parameter is power efficiency. The BPSK is more power efficient among the three, requiring the least transmit power for a given bit error rate, and QPSK requires more power than BPSK to achieve the same bit error, but it is more efficient in terms of bandwidth uses. As in M-array PSK, power efficiency decreases as M increases because higher order M-array PSK scheme require more power to maintain the same bit error due to their reduced noise immunity. Next parameter is spectral efficiency. BPSK have lowest spectral efficiency with 1 bit per symbol, whereas QPSK have higher spectral efficiency than BPSK with 2 bits per symbol. Spectral efficiency of M-array PSK increases with M as more bits are packed into each symbol. However, the trade-off is reduced noise immunity and increased complexity. And the last parameter is application. BPSK is used in application where simplicity and reliability are crucial, such as deep space communication and some form of wireless data transfer. QPSK is widely used in modern communication system, including satellite communication, mobile network like LTE and Wi-Fi, due to its good balance of performance, bandwidth efficiency and implementation complexity. M-array PSK is used in scenarios where high data rates are required, such as in higher order modulation scheme in mobile communication, for example 8 PSK in EDGE, or in system where bandwidth is crucial constraint. In summary, M-array PSK is versatile and efficient modulation technique that balances the need for higher data rates with the constraint of bandwidth and error performance. Understanding its principle and application is crucial for designing modern digital communication system. Thank you for joining this lecture.